So again, I was introduced this morning. I'm Dave Johnson. I'm representing the USDA's National Ag Statistics Service. I'm not a statistician. I'm a geographer, actually, so to use a statistical term, I'm a real outlier. So I'm going to be showing a lot of maps, less tables, and talking about remote sensing for crop production estimation. So at NASS, I sit in what's called the research division, and we have a group of us that are trying to get at using spatial analysis techniques, remote sensing, to add information into some of our monthly reports, particularly for crop production, which comes out the middle of each month during the growing season. We also do an area survey, which comes out at the end of June. It's shown on the left. And, we're even trying to feed into a weekly product called the crop progress condition, so using remotely sensed data for all those. Also, I have a lot of slides that were kind of sciencey, probably beyond the scope of this audience, which I wasn't sure what the audience was, so I'll be blowing through those. But one thing we're doing a lot of is land cover mapping. That's kind of the broad term, using satellite imagery. And what we're really trying to do is figure out what crops are growing where. We've been doing this for about a decade now, using imagery, mainly from a sensor called Landsat. Landsat is not new data. It's actually, this is a screen grab from a day or two ago. It's been up for 45 years. There's been 8 sensors. We're on Landsat 8 right now. Landsat 7 is still working. Landsat 6 went into the ocean after launch. So when people talk about remotely sensed data, drone data being the new thing, it's actually not necessarily a new thing. And it's data that anyone in this room can access and visualize, actually. It's provided by the U.S. government for free. NASA and the Geological Survey host it. Through a website called GloVis, you can pull up a Landsat scene. Landsat captures an image every 16 days throughout the Earth. It's in a polar orbiting, so it's constantly going, and as the Earth rotates underneath it, it collects imagery. This is a scene from just a few days ago. I don't know if you can see on this projector, a few high clouds. DC is where the crosshair is. If we zoomed in, the crosshair is at Poolesville, Maryland, a little bit up north and west of us. The data here in the bright greens, this is from the summer. The very brightest of greens, those are soybean fields. The darkest of greens, those are woodland areas, forests. And the medium shades of green are cornfields. I know that just from experience. And, again, I don't know how well they're showing up on these screens, but we can observe these types of data, and you can observe this type of data. So for our land cover classifications, we aren't just using Landsat, though, because we're actually an equal opportunity data ingester, and there's more than just Landsat data now. But in the center of the screen, on the upper center, is Landsat. The Europeans now are emulating what Landsat's doing. They do a system called Sentinel-2. That's some of the data over on the upper right. This is over a week's time period. Europeans, there's some commercial data sets called DMC. We're getting those. And in the lower right, it's actually from India, actually the country of India. They're collecting data too, and most of this data is free or low cost. They all have different attributes. Different spectral bands are collecting in spatial resolutions. Landsat's at 30 meters. The Sentinel-2 data is actually down to 10-meter resolution. The DMC is around 20 meters. ResourceSat's about 20 meters also. This is what it all looks like combined into one slide. So our challenge at NASS is to take all that information and try to make something useful out of it. And, of course, we have clouds. That's the areas in white. We can have areas where there's a huge rain event, and so we're seeing a lot of standing water that flows off the signal. We can also have smoke plumes, different seasonal timings of crops when crops are planted. So we have a data processing flow. All this data is stacked geographically, so different time periods we can put together. We use commercial tools, a bit of a yada, 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 but I'll try to explain that yada, yada, yada in this slide. On the left are 4 panels showing what we call false color infrared imagery. So areas in red are actually lush green fields because we're looking at the infrared part of the spectrum. We have April, May, June, and July. So that's what the satellite sees. We get some information, administrative information from a sister USDA agency that tells us what was growing in some of those fields. Those are shown in circles. So in this example, we have some almonds. This is in California. We have some barley areas, some pasture grass areas. The data trains on those known areas. We use a decision tree methodology. It's not really a statistical methodology, but decision trees, and then we can extrapolate out to the rest of the image to fill out what was growing where. Areas in red are cotton fields. How well are we doing? This is our first way we can measure how well we're doing. We withhold some of our administrative data going into the training scenario so that we then can look at those fields and see what the classification said. For most of our big commodity crops, the corn, the soybeans, the wheat, we do pretty well. And this table is an example from the state of Colorado, 2014. Corn, we're doing about producer and user accuracy of 90%. Another way of thinking of that is the opposite of producer's accuracy. Omission error is 9.24%. So we think we're omitting 9% of the time places that should have corn. And then conversely, we are committing corn about 9.78% of the time. So we might be putting a corn pixel into the middle of a soybean field. So we hope those numbers are balanced. We'd like them to be 100% perfect, but they're not. If they're balanced, we know we don't have too much bias. And then we can also come up with an overall accuracy of the scene. In this case, it's 85.5%. So if we were to throw a dart at that map and see where that dart lands, we could say 85% of the time that pixel is labeled correctly. So we have that kind of error assessment, but we can also, NASS in June is doing a huge area survey, about 11,000 square miles of area are enumerated, so people actually go out and document what's happening in these fields. It's typically a square mile. This is a hypothetical example, but in the middle of the screen there's a red box. That's a square mile. In the yellow, that's our color for corn. So classification said within that box is almost all corn. So we could say it was 637 acres classified. But the enumerator saw 640 acres. That's a square mile. So we have a discrepancy. We don't just look at one. You start to add it up. There's three things where we have what the enumerator said, what we classified it as. There's over 10 sites and so forth. We build out eventually a big regression between what the classification predicted in that field and what the enumerator saw in that field. And ideally, there would be no scatter along that one line. But this allows us to tease out outliers both in the enumeration, so where there was an enumeration error. It also allows us to tease out where we had a classification error. We throw those out, and we get what we believe is the ultimate area estimate with reduced variances. We have a system in SAS to do that. Like a close colleague of mine, Bob Steffren, does most of that work. We can do this pretty rapidly in time with a little latency, but it allows us to really drill down to the county level, where our surveys, we might have one sample in that entire county, but here we have very detailed information. With these different these satellite sensors, something I do a lot of in my work is trying to compare how they vary per sensor. On the left is from the Sentinel system. On the right is an example from the Landsat 8. Same area, same time period. The classifications look very similar, so it's good. The Sentinel has finer resolution, so this, if you can tell from the prior slide to this slide, we're getting finer detail. The roads are popping out a little better. Those are in gray. Again, yellow areas are what we think are corn fields. Green, dark green is soybean fields. So these are types of things in the data that we're looking at. Can that help us improve our statistics? Unfortunately, we don't think it actually is helping improve our statistics as we drive down to finer spatial resolution. These are the same sort of scatter plots, 60-meter classified data versus 15-meter classified data, and the scatter plots look very similar. This is for corn. I think if we have most of the fields we're looking at in the United States are pretty big in size. They cover dozens of hectares, dozens of acres, but we do expect this to be better if we were looking where there's real narrow fields, particularly in developing countries. A lot of this classification work gets used for more than just area statistics, but any number of research questions in terms of crop rotation, land cover, land use change effects throughout the United States. So we do give out that data. That was purely on the area side. On the acreage, or the yield side, which is actually where I spend more of my time, we're not able to use the Landsat system. We want to, but Landsat only gives the image every 16 days. If you add in a cloud probability of like 50%, so you might get an image once a month. And the crops are very ephemeral, to use a fancy word, versus people who study the forest. They're much more static. Crops are planted in this country usually in April and May. They green up, as you can imagine, and in September they're browning down and they're harvested. It's done. So if you don't capture any imagery within that time period, you have no way of capturing the yield or the area. So NASA has a different sensor, MODIS. which collects imagery almost daily. That the trade-off is it's not nearly the spatial resolution. So Landsat's 30-meter, MODIS is about 250 meters. MODIS has nearly a 20-year history, so it's been churning along. I should also say these are both science-developed sensors. They're really not for operational products, but people like me are taking these products and using them operationally in mass. MODIS data you can all visualize using a website here, Worldview or Earth Data. And just some subjective analysis you can do really quickly. This is from the summer, eastern South Dakota, western Minnesota. There's kind of a light streak going through that where I've circled in red. That was a big hailstorm that rolled through there. So this imagery was available the next day. You can zoom in a little bit. I can't here on this file, but so it's meeting the criteria for spatial detail and low data latency. Some more type events. We had a big snow event in the western part of the wheat belt this year, so western Kansas into Colorado up into Nebraska. That white band it's actually snow, it's not clouds. On the left, that was May 1st. 3 or 4 days later, May 4th, it had mostly melted. There are some clouds here and there in the scenes, but again, this was really easy to tell the folks within our crops branch, like, yeah, these are the counties you should be looking at in Kansas, and not all of Kansas was hit by snow, although the media might suggest that. Another example where we can use imagery for quick assessment that meets the timeliness needs and the spatial detail. We had a lot of water going down the Mississippi River, alluvial plain early this spring. So on the left is actually what it looked like before the water, and on the right is after the water. Areas in dark blue were inundated. That was still fairly early in the year, so it didn't probably have much impact on the crops because many of them had not been planted or had the opportunity to be replanted. But just another example. Through time series work, we try to distill. It makes our job easier if we can boil it down to each image to one metric, and we use often something called the NDVI, the Normalized Difference Vegetation Index. It's basically a proxy for how much biomass, how green the landscape is. There's even a wiki page for anyone who does vegetation-style mapping will know of this term, and it's particularly common in agronomy. Is that box? Oh, can I hit OK? Technical difficulties. I think we're OK. No, we're not. Are the people online still able to see the slides? While he's looking at that, that image was an example image of this normalized difference vegetation index for the United States. And as it comes back up, it wasn't just for a single day. It was actually the image was a composite over 8 days. So what we tend to do is to get rid of the clouds. We look at over a time series and distill down a full week's worth of data down to, we pick the best pixels throughout that time period for each point in space. And in this example, the areas in the lighter, well, white, those areas with high NDVI, so very verdant. Areas as you go west, more desertous in the United States, those are areas with low NDVI. I'm getting the error message again. So don't connect. I don't think this is the PDF problem. So taking these images through time and extracting only over the cropped field areas, this is what we'd expect to see for different crops. The time is on the x-axis, the amount of NDVI is on the y-axis, and the highest peaking one is soybeans. It has a very high NDVI in middle of August. Soybeans are planted later than most crops. Corn, which is in the golden color, more in the middle of the mix. And the light brown is winter wheat. That's planted actually the prior fall, so it greens up the earliest. But these are the types of signals we're looking for within the remotely sensed imagery. This is derived from remotely sensed imagery. And they can shed a lot of information in a timely manner. This year showing some NDVI profiles, what happened in the United States. Very good crop year for corn. We actually met a just above a record yield. Started off kind of sketchy. We weren't sure. It was the late startup was shown in the red line. The bottom there, just for grins, or not grins, but Puerto Rico, as we all know, it was massively hit by hurricane. The NDVI in Puerto Rico, basically the trees were just shredded. If anyone's looked at any high-resolution imagery there. So the MODIS sensor is picking that up. So that's not really a crop example, but it's the type of things you can see with NDVI. I'm going to go a little bit more quickly through these. Basically, from the satellite remote sensing perspective, most of us are trying to build an empirical model. So we take historical statistical information. So for me, it's what NASA's published in the past. Well, it could be at the national level or state level or county level for yield in this case. And then we look at the historical imagery that was available during that time, and we build relationships and how this model works is a whole talk into itself, or really a day's talk. But these relationships allow us to build maps of what's going on, either currently or even retrospectively. I'm not allowed to show the 2017 map in detail. Maybe I can a year from now, but we do have some confidentiality. But this was 2014. I kind of consider a normal year. Areas in the greens and blues, if they're showing up on the monitors, were higher yields. Areas in red were lower yields. That was 2014. 2012, a big drought year in the United States. Corn yields were down about 20%. This map, which is completely modeled from MODIS data, is picking up on that. Particularly out west, where it was really dry. Nebraska is about half irrigated, so many of those fields are okay. But zooming in on it, a map like this, again, getting at the low latency and high spatial detail. A hailstorm rolled through this county in central Iowa. I can't remember which year it was, but we're able to pick that up from remote sensing. Again, there might have been 2 or 3 survey points within that county, and you could easily imagine missing that hail event. What's really helped the remote sensing community lately is, well, we struggle just with data volumes and compute, but a lot of stuff is getting cloudified, so to speak, or put it, big data in the cloud, where we can take our algorithms to the cloud and run the processes and return the answer instead of having to download literally terabytes or tens of terabytes or hundreds of terabytes of data. USDA Foreign Ag Service is an example where they have a site where the MODIS data is on there. You can drive out data products. And they really allow someone to generate some pretty simple models that work pretty well. For corn yields in the United States at the national level, if you integrate under the curve but over a threshold and compare that to historical yields, you get a model with a very good, what I call a very good model, 0.92 R squared. This is showing 3 different models. On the left is just trend. In the middle is this integrative model. So standard error of 4 bushels. What typical bushel, average bushel in the United States is about 170. If you just looked at a trend model, the standard error is about 12. So bettering that trend model by 3 times. Some people like to look at the max of the NDVI and relate that to yields. That model is not good as integrating, but it is better than the trend. This works at not only the national level, but the state level. So Minnesota, South Dakota, Nebraska shown here. Pretty nice models. And these models can literally all be derived or updated in like 10 minutes. It's very simple. So it works at the county level too. It still produce map output. Maybe I rushed a little too fast, but some of the strengths and the weaknesses of this, and trying to get at some of the questions that were being asked for this panel. What are the strengths of remote sensing? It should be caveated. Remote sensing is best when you're looking at things on the land or on the surface of the earth. So it's not going to probably get at economic or demographic type information. But strengths, good aerial coverage. And these satellites are not just covering the United States, they're global systems, and they have been for a while. They have a very good temporal revisit rate. Landsat is only 16 days. We wish we were a little faster than that, but MODIS is daily. There are other sensors that are around that week's time period. So we don't have to anticipate one data point every 6 months or every year. Many of these data sources are becoming free. The United States was kind of the first to do this, but even the Europeans are doing so. Most of these sensors have little data latency, and it's, I think, what the remote sensing community has done the best. When the product is captured today, it's probably available tomorrow, if not tonight. So there's been a real emphasis on getting the data out there. In my mind, it's most useful immediately, and it's also very useful like in a real historical perspective. So those images that are 45 years old are very valuable too. You know, we can really drill into the spatial detail. And then the cheap computing aspects now have really helped. All this data is now sitting on servers like Google and Amazon, and we're able to leverage that to some extent. So the weakness is this is still computationally intensive, and it really takes an integrated skill set. You got to know how to code. You got to know something about geography and agronomy, and there's a lot going on. So I think the best person is kind of a jack of all trades. A weakness is the calibration of these data sets. So through time, they're collected, and at points they say, oh, we can actually reprocess this old data and make it better. So every once in a while, the NASA community, the science community says, yeah, we're going to reprocess the whole data series. And they're going to do it again. I can tell you that. Like Landsat was just reprocessed in a year. They're going to improve the geometry a little bit. They're working on that code. And it's going to be reprocessed again. So that means you have to rebuild all the models. The measurement of the uncertainty of the data is not very well established. So I was using the NDVI example, and you may say, well, how good is that NDVI? Is it plus minus 5% or 1%? And it's really hard to say. You know, it's probably within a couple percent, but there are not objective measures. These satellites can capture temperature. A lot of times you'll see the thing, it's within a degree Celsius. That's a bit of an estimate. There are studies where they try to calibrate this with in situ data, but there's always some caveat. Oh, we only did it over desertous areas, or we only did it in the spring, or over certain land cover types. And anyway, to me, there's not a long-term history. 45 years is actually pretty long, but NAS has been going on for over a century. So things we develop, NAS can look at skeptically because it's like, well, we need to have decades worth of history. And I think I'll wrap it up with there. The past utility of remote sensing was probably a little oversold, but the tools really, really are getting better now on the data set. So thanks. Hopefully that was interesting at least.